Start recording. And I said we probably use a calculator, so let's do that. Bye, Mia. Bye. You too, thanks. All right. And away we go. Let's clear this. Today is somewhat of review, which is good, kind of since we have the long break. Not a bad time to start a section that we've kind of already covered before. It says use a calculator to find where the velocity is positive and negative and where the speed is increasing and decreasing. And they show us, they give us the velocity. So we go to y1, we'll use a calculator for this. T squared, or in this case x squared, minus 8 divided by t plus 1 squared. Yeah, that looks right. And the window that we're going to use is 0 to 5. Yeah, because 0 to 5 because of this. So we're including 0. We're including 5. And you got to go from negative 10 to 30 to have this equation fit nicely so that we can actually see the values actually to the right side. So 0 to 5 and negative 10 to 30. And when we graph, this is what we get for the velocity equation. So let's see, velocity is positive and negative. So positive and negative. And we need that 0, so we're going to go second, calculate. Number 2 is the 0. And let's go over and get this 0. So we need to see y needs to be negative. There we go. Then y needs to be positive. There we go. And back up a little bit. So 1.254. So we have positive velocity from 1.254 to 5, and we're including 5, and velocity has a positive value over at 5. Matter of fact, we could even calculate that value at 5. See, it has a positive value, 24.77777. So we're going to include 5 in that positive velocity, but not the 1.254 because the velocity is 0 there. So negative from 0 to 1.254, and we're going to include 0 again, or in this time because, well, 0 has a negative velocity. It's negative 8, actually. Speeding up and slowing down. Well, now we need to compare the velocity and the acceleration. So we can do this. We can go math number 8 is derivative. So math 8 is derivative. We're going to take the derivative with respect to x, and here's where you have a choice. Here's where I could save you a little bit of time. You can either put the equation back in, or we can use y1. And we can do that by going to variables, V-A-R-S. It's down here, right below your kind of the arrow keys. Variables, and then if you arrow over to y variables, and we're using function, y1. So there's y1, and now y1 is in there. So we're taking the derivative of the equation that's in y1. And once you learn it, it goes really quick, and now you don't have to re-enter the equation. And then we're evaluating all the derivatives, or the derivatives at all x values. So their x goes in there. So now we can compare the velocity and the acceleration and decide if we're speeding up or slowing down. Now it makes it nice that the acceleration is always positive. It's always above the x-axis. So speed is increasing when both the velocity and the acceleration are positive. So that ends up being 1.254 to 5. And since the acceleration doesn't add any zeros to this, it never goes from positive to negative, then it ends up being very similar answers. So the speed is decreasing from 0 to 1.254 because the only 0 that we have to worry about is the 0 for velocity. So if there's zeros for acceleration, then this problem becomes a little bit more complicated. But it's a comparison of acceleration and velocity to decide if it's slowing down or speeding up. That's, of course, part of this section, but this is really, example 2 kind of gets to the heart of what we're doing today. Find position from displacement. If you have initial position, and you add on your displacement, that's going to equal your final position. And that sentence means everything. That sentence right there is kind of the heart of what we're doing today. If you live on block 2 and you walk 8 blocks, your displacement is 8, you end up on block 10. So your initial position plus your displacement equals your final position. So suppose the initial position of the particle in example 1 is s of 0 is 9. What is the particle's position at 1 and 5? So position at 1 would be 9, our starting position, plus the displacement from 0 to 1 of v of t dt, dt. Well, that's it. It's 9, the initial position, plus your displacement. That's going to be your final position. So we can go 9 plus, on the home screen, math number 9, from 0 to 1, of, now we can type the equation in again if we want, but if we can go to variables, y1. There we go. We have it still sitting in the y equals. And we're doing this with respect to x. So here's our final position, 5 1/3. 5 1/3, or 5.333. S of 5 now is equal to 9. We're still starting at 9, but now our displacement is 0 to 5. Now the reason I'm starting at 0 is because that's the value they gave us. If they said S of 1 equals 9, then we would go from 1 to 9. All right, what is that? Oh, 0 to 5, okay. V of t dt. So now we can go up there, grab this, and then just change this to a 5. 5. There we go. 44. That ends up being a nice number. 44. So initial position plus displacement gives you the final position. Any questions on this? All right. Calculating total distance. Find the total distance traveled by the particle in example 1. All right, total distance now, the area under velocity is the total distance. So if we're going to do this by hand, and we're not going to, but I'll set it up, 1.254. So we'd have to integrate from 0 to 1.254 of v of t and take the absolute value, plus the absolute value of the integral from 1.254 to 5 of v of t dt, like that. Because at the beginning, let's see, what do I want? I want the graph. If you look at the beginning of the velocity, we'd have negative area to begin with. I'd have a negative value for that. And then after, I'd have a positive value. But we want everything to be positive. So what's the concept here? Well, if you walk 6 feet to the right, 6 feet to the right, and then 3 feet to the left, your displacement was 3. But you went 6 and 3, you traveled 9 total to get to that displacement of 3. So now we're saying, all right, we know the displacement, now how far do you have to walk to get to that displacement? What's the total distance traveled? So we want everything to be positive. And we could do this individually. Or, if you're allowed to use a calculator, I certainly wouldn't do this. I would just integrate from 0 to 5 of the absolute value of v of t. And what that does is any negative y values we have for v, those become positive, and all that negative area becomes positive. So we're going to go math number 9, 0 to 5 of the absolute value. Math num, right? Yeah. Absolute value of variables, y equals, or y1, with respect to x. What's nice about using that little technique is I'm using the equation over and over and over again, but I really only had to enter it one time into y1. So here's the total distance traveled, 42. 42.586. Modeling the effects of acceleration. A car moving with initial velocity of 5 miles per hour accelerates at the rate of 2.4 t miles per hour per second for 8 seconds. So they give us the acceleration. A, how fast is the car going when the 8 seconds are up? So we need v of t. v of t is equal to, well, that's the acceleration, so 1.2t squared plus c, right? The antiderivative of that. We add 1 to the power, so we need to take 2 times something to get 2.4. That's the 1.2. A car moving with initial velocity, so that means we have the 0.05 for velocity. So 5 is equal to 1.2t times 0 squared plus c. So we plug that initial value in. So c ends up being 5. V of t is equal to 1.2t squared plus 5. So I won't do, oh, it's way off. Ooh, that was weird. Hold on. It's like, why can I not see that decimal? All right, but did we answer the question? How fast is a car going when the 8 seconds are up? Now, v of 8 is equal to 1.2, 8 squared plus 5. So 1.2 times 64 plus 5. So 81.8. Woo, flying. 81.8 miles per hour. How far did the car travel during those 8 seconds? So in other words, for letter B, we're going to, we want s of t is equal to the integral from 0 to 8 of 1.2 t squared plus 5 dt. Now, that's the displacement because it says how far did it travel. So I'm not worried about, it doesn't say where did the car end up. It was at mile marker 200. Where did it end up? It's just saying, well, how far did it go? That's displacement. How far did it move? It's not asking about position. So I don't need an extra value for this problem. If I find the area under the curve of velocity, this is the displacement. In other words, how far did it travel? So math number 9, 0 to 8 of 1.2 t squared plus 5 dt. So 244. 244.8 miles. So they gave us acceleration, we backed up to velocity, then we backed up to position using integral both times. That's a big deal. That's a big deal. That's a big concept. Accumulation of waste. This is all story problems involving rates is the category that I've given this. So I have a whole category of free response questions for this topic. An expert has predicted that the rate at which waste will be deposited at a small landfill from 2020 to 2030 can be modeled by the function, where W is measured in tons per year and T is the number of years since the beginning of 2020. So that's the 0 year. To the nearest ton, how many tons of trash will be deposited in the landfill from the beginning of 2022 through the end of 2023? So if this is the rate, and they ask how many, that's actually position. So they've given us the velocity of trash being collected. Now they're asking us how much. That's backing up to position, like I said. So we're going to do integral. If 2020 is the 0 year, then 2022 will be the 2nd year. Now this gets a little tricky. If it's through year 2023, what's the top number going to be? What do you guys think?
4.
That's right, 4. Because we got all the way through that 3rd year. So we've gone to the 4th year. So 2 to 4. I think it would be very knee-jerk reaction to put the 3 up there. I'll bet that's a common mistake rather than a 4. So a little tricky. And then we have W of T dt. So let's get the answer. Math number 9. 2 to 4 of, let's see, 450 times, I don't want second, times 1.043 to the T dt. We're going to use x's here. All right, 1021. I think it says it around here, to the nearest ton. To the nearest ton. So 1,021 tons. We always round to 3 decimal places unless it says otherwise. So that is an accumulation given the rate. We're going to practice that a lot. From noon until 6, the rate at which people enter an amusement park at time t is given by E of t. So E of t is enter. And I would write that nice and big when you do these story problems so that you don't have to keep reading through the problem, because you'll want to know how much entered, how much left, and you want to know. And L is left, so that's good. For which the graph is shown. Oh, I put the graph on here, and I must not have saved it, because I remember I forgot. I went back, I put it on there, and it ended up not being on there. So give me a second here. This is a little, I got a timeout on the field. So if you're actually watching this at home, you could probably fast forward a little bit, because all I'm doing is grabbing the graph. "20 clicks and I'll be there. Your password is at risk. That's fine. I'm sure I'll be all right." I don't think my password to this has a big street value. E-text. E-text. I wouldn't bother with this if it wasn't such an important problem. If I felt I could skip it, I would. All right, 7-1. This is example. Where'd it go? Oh, there it is. I need example 6. All right, example 6. Close that. All right, there's the graph that I needed. Should I grab it? Let's grab it. And it's going to be huge. Send to current page. Boom. That fit? No, it's going to get tiny. Okay, we can read that. There it is. And that's in your book. This is right out of your book. So that's the graph of people entering, the rate at which people are entering. So this is enter. And we have people are also leaving at a rate of this equation right here. If 3,000 people are in the park at noon, how many people are in the park at 6 p.m. rounded to the nearest multiple of 100? So we start with 3,000. If this is the rate at which people are entering the park, then the area under the curve is how many people are entering the park. So we need the area under the curve, and we're going to break this into a trapezoid to start out with, which, let's see, that's going to be plus 1/2 times 3 would be the height, and then the bases would be 400 and 600. Plus, we have just a rectangle right here. This is how I'd break it up. 1 by 600, so 600. And then we have this trapezoid right there. A 2 1/2 times 2 would be the height, and then 600 plus 500. So there's entering. But then we got to minus out the people that are leaving. So here's the people that are leaving. And we're going to integrate from 0 to 6, because we're going from noon to 6 o'clock, of 52 plus t squared e to the negative t divided by 5. I could have just written L of t. That's probably what I should have done. All right, so now we got some calculator work to do. We got 3,000 plus, let's see, 1/2 of 1,000 is 500, so 3 times 500, 1,500. Plus 600, and then plus at the very end is 1,100. So if nobody left, there'd be 6,200 people. But people have left. So we're going to minus math number 9, 0 to 6 of 50 times 2 plus, I can't read my own handwriting. I think that says t squared, e to the negative t divided by 5. Do I need an extra parenthesis. I think I got it. There we go. So 4,009, how many people in the park? Round to the nearest multiple of 100. So about 4,100 people are in the park. That's kind of a big concept. You might get an equation that is entering, an equation that's leaving. I have several examples of those that we will be doing over the next few class days. We're going to spend a lot of time on this section, comparatively speaking. Oh, and we're going to kind of, we've gotten to the point, you guys, where I expect you to know how to do some of this stuff. Like, I'll expect you to know how to do integration. I'll expect you to know, and I'll give it away here, we're going to do the trapezoid method. So I don't think it's worth our time, at least on the lecture part, to stand here and type a bunch of numbers in the calculator that I assume you know how to do. Now, if you don't, then that's something that you might have to practice. But here's what I'm talking about. A pump connected to a generator operates at a varying rate, depending on how much power is being drawn from the generator to operate other machinery. The rate in gallons per minute at which the pump operates is recorded periodically over 60 minutes as shown in the table 7.1. How many gallons were pumped during that hour? Well, this is the rate. It says that's a rate. So if they're asking for how much or how many, that's really position. So we're backing up. Now, backing up is integral. Integral is area under the curve. But we don't have an equation to integrate. So the best we can do is either LRAM, RRAM, or trapezoidal method. Now, trapezoidal is the most accurate of those three. So let's do trapezoidal method to find the area under the curve, because that's going to be our integral. So we're going to do one. How about we factor out a 1/2 from everything? Every trapezoid will have a 1/2 in it. It's 1/2 the base. The base 0 to 5 is 5. Or excuse me, the height. I meant to say the height is 5. And then one of the bases is 58. The other is 60. So there's the first trapezoid that we're estimating the area under the curve. Plus the next one, 5 to 12, is 7. And then we have 65 plus, 60 plus 65. And then plus, we're going to keep on going. We'll keep on going in that manner. The next height is 8. The next height is 3. The next height is 10. The next height is 7. The last height is actually 20. And then we have 59 and 63. 59 plus 63 for the two bases. And we would type all of that into our calculator. It'd take a while. This would be tedious. But I'm just going to give away the answer. I assume you know how to type that into your calculator. 3,550 gallons. The point on this one is that if you're given a chart, you're not going to be able to actually do integration to find area under the curve. We got to use LRAM, RRAM, MRAM, whatever they ask, trapezoidal method. If they don't say which one to use, trapezoidal is one of the most accurate. Simpson's rule is actually the most, but we usually stick to the trapezoid. All right, we've already done this because we kind of teach this early. Earlier in the year, it asked for describe the motion of the object, and then it just went into this paragraph of describing the motion. But we like to have it a little bit more organized. And in this chapter, they do. They do a very organized way of doing this. So we teach this a little early. Anyway, the function v of t is the velocity in meters per second of particle moving along the x-axis. Use analytic methods to do each of the following. In other words, work this by hand. A, determine when the particle is moving to the right, left, and stopped. So A, we like doing stopped first. We like to get our zeros first. So then we're going to find out when this moves to the right, when this moves to the left. So this shouldn't not a whole lot new here. 0 is equal to 6 sine of 3t. So we're going to set the velocity equal to 0. Divide by 6 is 0 still. And really, if I wrote everything out, now we're going to take the inverse sine of both sides. So this asks the question, where is sine 0? Sine is 0 at 0, pi, 2 pi, 3 pi, whole bunch of places. All the pi's sine is 0. Then we divide by 3, but we got to keep in mind that we're only going from 0 to pi over 2. So we divide by 3. 0, pi over 3 is between 0 and pi over 2, but 2 pi over 3 is past pi over 2. Here's pi over 2, here's 2 pi over 3, so we've gone too far. That's how I do those. When you have something other than 1 here, something other than 1, I just list out a whole bunch of them and then figure out when I've gone too far. And it's usually a nice little technique to find all the zeros. So it stopped at t equals 0 and pi over 3. Now we're going to do a number line, and we're going from 0 to pi over 2. So we have 0, which happens to be a 0. That doesn't always happen. Pi over 3, and then we got to stop at pi over 2. Pi over 2 is not a 0, which is good. I like that. So what's between 0 and pi over 3? That would be nice. Pi over 4 would be in there, yeah. And we can actually use pi over 2 because that's in the interval between two zeros. So there'd be a 0 here. Pi over 2 is not a 0, but there would be another one over here if we wanted to find it. So pi over 2 is something that we could actually use for this. All right, now if we plug pi over 4 in here, sine of 3 pi over 4, 1, 2, 3. Well, the sine is still positive times 6 is still positive. If we plug pi over 2 in there, we get 3 pi over 2, which is negative. So now negative. All right, we're moving to the right on 0 to pi over 3. And we're moving left on pi over 3 to pi over 2. But pi over 2 is not a 0. That actually has a negative value there. The velocity does. So it's moving left there. B. Find the particle's displacement for the given time interval. If s of 0 is equal to 3, what is the particle's final position? All right, determine, so 0 to pi over 2, determine the displacement. All right, so the displacement is equal to the integral from 0 to pi over 2 of 6 sine of 3t dt. That's displacement. So yeah, we got to do antiderivative. That's going to be negative 2 cosine of 3t. And we're going to go from 0 to pi over 2. All right, negative 2 cosine of 3 pi over 2 plus 2 cosine of 0. Cosine of 3 pi over 2, that's 0. So it's 2 times 1. So the displacement is 2. It says, it gives us an initial position, and then it says, what is the particle's final position? So final position would be, what does it say, 3? 3 plus integral from 0 to pi over 2 of 6 sine of 3t dt, because we would have initial position plus the displacement is equal to the final position. But we already did that work. 3 plus 2, 5. So the answer is just 5. We just add the two numbers together. That's what we did for this. We'd have the initial position, we add the displacement, that's equal to the final position. Now, the last question they ask is find the total distance traveled by the particle. So yeah, it ended up at 5, but how far did it actually have to go to get to 5? Even though the displacement is 2, it could have had to have walked a lot longer, a lot more to get to that 2. So that's what we're going to try to find next. All right, here we go. We should do one completely. Maybe we'll do the rest by hand. So total distance. Is there a letter C? Yeah. C. Total distance. But the good news, we've done a lot of work for this already. This is going to be equal to the integral from 0 to, I need any zeros from 0 to pi over 2, because we're going to split it over that. And we're going to take the absolute value. So we got to split over pi over 3 of, can I just write v of t? Yeah. V of t dt. And we're going to take the absolute value in case that, that distance is negative. I want everything to be positive now. Plus the absolute value of pi over 3 to pi over 2 of v of t dt. So there's the total distance walked, or traveled. I don't know if the particle's walking. But we've done the work for this. We've done the antiderivative. The antiderivative is sitting right here. All right, here we go. So we're going to go absolute value of negative 2 cosine of 3t from 0 to pi over 3. Absolute value. Plus absolute value of negative 2 cosine of 3t. And we're going to go from pi over 3 to pi over 2. Got to split it over the zeros. So negative 2 cosine of pi, because if I plug pi over 3 in, the 3's are going to cancel, plus 2 cosine of 0. Plus negative 2 cosine of 3 pi over 2, because we're going to plug the pi over 2 in, and I'm going to run into that, plus 2 cosine of pi, because the 3's will cancel. All right, we're almost done with this one. Cosine of pi is negative 1, so that's going to be 2. Cosine of 0 is 1. 2 plus 2 plus cosine of 3 pi over 2 is 0. But cosine of pi is negative 1, so negative 2. This is where we really needed those absolute values, signs. So that negative 2, where we walked left, is counted as a positive. So 4 plus 2. So the actual distance traveled was 6, even though the overall displacement ended up being 2. Walked 4 to the right, walked 2 back to the left. So a total of 6. Questions on that? All right. I actually want to get to this one for sure. As I'm recording this, on the day I recorded this, we are getting out at 2:20 today because we're right before Thanksgiving. 44, that's right. How do I have a? Okay. Kind of running out of time. This is taking a while. The graph of the velocity of particle moving on the x-axis is given. The particle starts at x equals 2 when t equals 0. All right, so there's your initial values. So there's the initial position when the time is 0. Find where the particle is at the end of the trip. Well, this is the velocity. So here's what I want. Where's the particle at the end of the trip? So initial position 2 plus the integral from 0 to 10 of v of t dt is going to be what I want. That's going to be the final position. Its initial position plus the displacement is equal to the final position. So we have 2 plus. Now the integral of v of t is the area under the curve. So we have a triangle. 1/2 times 2 times 3. Oop, not plus, because now the area is underneath the x-axis. Minus, we have a trapezoid here. What's the height? The height is 3. 1/2 times 3 times 1, 2, 3, 4, 5 plus 1, 2, 3 plus this triangle. 1/2 times 3 times 3. All right, we got the extra 2. So we got 2 plus half, that's 6, 3. Half of 8 is 4, minus 12, plus 9 halves. Great, we got a little fraction to deal with. 5 minus 7 is or 5 minus 12 is negative 7, plus 9 halves. That's negative 14 halves plus 9 halves. I'm getting negative 5 halves for the final position. Where is the particle? Negative 5 halves. It ends up being negative because of this big negative area, right? It traveled to the left a lot. B, find the distance, the total distance traveled by the particle, and that's actually the absolute value of these values right here. So we just want this, we want this trapezoid to be positive, so we're going to take 3 plus 12 plus 9 halves. Now we're not going to include the 2 because it didn't travel the 2, it started at the 2, so we don't include that. So 30 halves, because 15, right? 15 plus 9 halves. It actually traveled 39 halves to get to negative 5 halves. It went forward a little bit, it went backwards a little bit. So the displacement and the total distance traveled are not going to be the same. And then finally, one last comment. Everybody got it? Everybody good? One last comment on this problem is the displacement you'd have to integrate t minus 2 sine of t dt from 0 to 4. So this would be tabular. I expect you to know how to integrate this stuff. So we're not going to officially go over integration anymore. I'll do them in examples. I'll give you reminders. I'll give you hints for tests. But as far as going over the integral, we're done with that. We're done teaching that. Now, we'll still review as we go, but some of these problems, I'll just expect you to know how to integrate it. This would be tabular. It'd be t minus 2, 1 and 0, sine, negative cosine, negative sine. You draw the arrows, plus, minus, and you'd continue on, but we're kind of out of time. Go ahead.
On number 20.
Number 20. Okay.
On B, it says, so the total distance, you don't add the initial.
Okay. If you lived on block 2 and you walked 8 blocks and you ended up on block 10, the total distance you traveled was 8, right? Yeah. Not 10, because you wouldn't include where you started. You'd traveled 8, and that's the same concept here. So we don't include the 2 because we didn't travel 2, that's where we started. Okay, good question. All right, anything else? That's our time.